Please title these notes Geometric Applications 5 Notes, Volumes of Solids with Known Cross-Section. So there are a couple of prerequisites that you should write down. By the end of this lesson, we should be able to find the volume of solids with a known cross-section. But before we do that, we have to know some basic areas and volumes in a non-calculus manner. So make sure you have all these prerequisites written down. Most of them you know. The area of equilateral triangle is probably new. There's a way to figure this one out just based on your other formulas, but it's a pain in the butt, so if you just go and memorize it, that's probably easiest. Area of a square we know, side squared. Area of a rectangle, length times width. Area of a semicircle, pi r squared over 2. Be really, really careful. This is going to show up. This distance right here is r, not the entire diameter across the bottom. Area of a right triangle, base times height divided by 2. And area of an equilateral triangle, square root of 3 over 4, side squared. So an equilateral triangle, all of these sides are the same, so any one of them, same as all the others, just square it and you're good to go. So before we do the calculus way of doing things, we need to know how to work with volume in a non-calculus way. So let's do another prerequisite. So whenever we have a prism, let's just say it can be any like weirdo shape that we want. Let's do something like, let's say this. So it's going to be the same shape all the way up to the top. At least insofar as my artistic abilities allow. And what we've got is that the volume of this prism is going to be the area of the base times the height. I'm going to call this height the width because that's going to be consistent for the language that we've been using in the past. So even though you know this as area of base times height, just call it the width. It's the same idea. This is the base, this area right here, whatever the funky shape is. And then the height or the width is this right here. So this is true for everything. Whenever we have a base, whatever that area is, we're going to multiply by the width or height, however we want to think about it. So let's do some problems. We are going to write an expression for the volume of each of the following prisms. First, let's start off with a prism where the base is a square. With side T. And the width, let's label that Q. So if I'm going to draw that, that just means I have a square and side S there, width or height of Q. So the volume is just the area of the square times the width. Or, since we know the area of a square, oops, I said this side was T, not S. T squared times Q. Pretty straightforward, also really, really critical. So let's do a few more of those. I just want to make sure you're good to go with all of them. I'm also going to draw these in different orientations. You should be able to find these volumes no matter what. So we're going to say the base is a rectangle with one side x, the other, that says other, side of x plus 3, and a width of z. So let's say our base is over here this time. So here's a rectangle. One side's x plus 3, and then the width, we'll let that be z. So our volume is just going to be the area of the base times this z, which is the width. Same idea if the base is a semicircle. With a diameter x, and the width is dx. You might get a sense looking at this of where we're going with this. So I'm going to go ahead and I'm going to draw my semicircle. So this diameter here is x, and then I'm going to draw a little prism. This width here is dx. And so if I'm going to find the volume, it's going to be the area of this base. However, we got to watch out because the area of a semicircle is pi r squared over 2, but the radius is this part right here, whereas here x is this entire diameter. So if we want to take that and we want to make it into a radius, the radius part is right here. This is half that distance, x over 2, and that's what we're going to be using in the formula. So the volume is pi r, which is x over 2 squared. Don't forget your other over 2. And this is again the area of the base times the height or width, which we said was dx. Two more with triangles, and then we'll get into our calculus-y end of things. So let's say we've got one where the base is a right triangle with legs of 3y and y plus 1. The width is dy. Well, I'm going to go ahead, let's draw base, that's a right triangle, and then go up. Here's our other base. I'll extend that out there. Okay, so we're saying that the legs are y plus 1 and 3y, and that the width or the height is dy. So that means that the volume is the area of this base, so 3y times y plus 1, and that was divided by 2. Base times height divided by 2 being the area of the triangle, and then times dy, so this was area of base, and then width. Final one is using our new-ish formula. The base is an equilateral triangle. With side S, the width is ds. So just for kicks, I'll draw it over here. So that's my best shot at an equilateral triangle. One side is S, meaning all the sides are S, and then we can go and make that into a prism. And we're told that the width or the height is ds here. So our volume, once again, is the area of the base, which, if we look over here, root 3 over 4, side squared. And then the width was ds. So those are the pieces that we need to do these problems. Now we just have to figure out how to put them together to do volumes of solids with known cross sections. So this is the real meat of what we're doing today. Here's an example of the type of problem that we're going to see. Find the volume. Notice that we're doing volume now instead of area of the solid whose base is the area in quadrant 1 that is bounded by f of x equals x, g of x equals x squared, and whose cross sections perpendicular to the x-axis are squares. So what this is doing is this is building off the work that we've done earlier in area, because notice that it's talking about a solid whose base is the area in quadrant 1, blah, 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 blah. If we just look at this section right here and not this last part or this first part, this is something that looks pretty familiar. So what we're going to start off by doing is we're going to start off just by sketching this area just like we would have done before. So we're looking in quadrant 1, so that's up here. F of x equals x. G of x equals x squared. Let me redraw that a little bigger. So we're looking at this area right in here. And when this says perpendicular to the x-axis, that means if our x-axis is here, any little rectangles, cross sections, anything we're talking about is going to be there. That's our cross section. There. So what this means is it means we're setting this up very, very similar to what we did previously. We're going to have our little infinitely thin rectangle right there. We've got this width of dx. So far it's looking really, really, really similar to what we did for area. What's different is that now what we're going to do is we're going to take this area that we have here and we're going to draw cross sections coming up from it. Basically, instead of having a rectangle where we find this two-dimensional area, we have infinitely thin little tiny prisms that we're going to find the volume of this infinitely thin little piece. And then we're going to add up all the volumes, just like we added up areas earlier. So there's a nifty little demonstration of that. So let's say here that this was the area that we had it shaded in. So what's happening is that from each infinitely thin rectangle that we draw here, there's a square that's coming up out of the screen to form this kind of weird solid. So if I grab it and I twist it up, we can kind of see right here, it's sort of going up to form this square, and then each point later on, we're seeing that same square that's based on this distance right here. So a whole bunch of little squares I can keep rotating and kind of get a sense of that shape. But the idea here is that these cross sections coming up out of the page are squares. We could also make those cross sections be semicircles. So here, if I twist it, you can see that's a semicircle coming up out of the page. And we've got a whole bunch of little semicircles coming up like that. Could turn those into equilateral triangles. Here you can see they're nice and pointy like that. There are those equilateral triangles coming up. Rectangles if I wanted. Same ideas. So going back to our problem, an enormous amount of this is going to be the same as what we did for area. There's just a little twist at the end. So I'm going to set this up. Volume is going to be really similar. It's going to be from our starting value to our stopping value. We're still going to have our width at the end. And we're going to find those the same way that we've done before. There's going to be a little something different right in here. I'm going to hold off on for just a second. But let's start with finding our stopping and starting values. So same thing, we set these equal to each other to find the intersections. So here this x-coordinate is 0. Here this x-coordinate is 1. And so we're starting where x is 0, we're ending where x is 1. We have a dx. What's going to be different is that instead of this part right here being simply the height of this, it's going to be the area of the base. Times the width. That says area of base and we're still going to need what we found earlier in terms of this height here. So this is still top minus bottom, so f of x is this first one here minus g of x, so x minus x squared. I'm going to mark that right here. But now, because these cross sections perpendicular to the x-axis are squares, instead of just putting this x minus x squared in right here, I'm going to say that this is the base of a square that's coming out of the page, kind of like that. I'm having this sort of infinitely thin square that's going to be the base of my prism. What's the area of this base? Area of the base? Well, I know what the area of a square is. It's just sides squared. And I know that my side is this x minus x squared. So where this is coming from is I'm saying that the area of this square here is side squared, and I know this side is this little height that we found when we were doing area. A quick bit of calculator usage later, math 9. So we have x minus x squared, quantity squared, comma x, comma 0, comma 1. Ta-da! All done. So let's write out our steps before doing the next problem. First thing is to draw exactly what you would for area. Remember, perpendicular to the x-axis means draw your little rectangle like that. Perpendicular to the y-axis means you're going to draw it like that. So make sure you do those little drawings just like you would for area. You're going to set up your start, stop, and dx or dy values just like for area. Where we start having slight changes is you're going to label the height of your rectangle on the drawing rather than putting it in the equation, because our equation is going to change a little bit. Write your expression for volume using integral from start to stop, area of base times width. So let's see what that looks like on another problem. Find the volume of the solid whose base is bounded by f of x equals negative x squared plus 4 and the x-axis, and whose cross sections perpendicular to the x-axis are semicircles. So I'm going to start off by just paying attention to the base, which is bounded by, so draw that just like normal. Negative x squared is an upside down parabola, plus 4 moves it up 4, so here's my f of x. Here's the x-axis. So remember, this x-axis is just the line y equals 0. So we can say f of x is negative x squared plus 4. We can say this x-axis is the line g of x equals 0. And the base is this area right here. I'm told the cross sections are perpendicular to the x-axis, so I'm going to draw my line here like this. This is a dx, just like we used before. So I'm going to set this up. It's going to be volume, but it's going to be a dx. And I'm still going to find my starting x and my ending x, so I can find those bounds by setting this and this equal to each other. So this has an x value of negative 2, this has an x value of positive 2. So my bounds are from negative 2 to 2. And now if I were doing area, I would just find this height and put it right in there, but I'm not. So I'm just going to find this height and I'm just going to label it right here. So this height is still going to be the top function, so that's f of x minus the bottom function g of x. We know f of x is negative x squared plus 4, and g of x is 0, so minus 0 just gives us that same thing. Now, remember that for volume, we're going to go start to stop of the area of the base times the width. We've got all of that except for the area of the base. And let's remember that a semicircle, the formula is going to be pi r squared over 2. Because it said that their cross sections are semicircles. Now, I have to figure out what this looks like. So I'm going to have basically little tiny semicircles coming out of this, with this sort of as that flat side. And so I have a whole bunch of little tiny semicircles coming out, but this is the one that I'm looking at in order to set up my formula. Now remember, the r is this distance right here. So this pink distance is negative x squared plus 4. If we cut that in half, we're going to get our r, and we can put it right in that formula there. So our volume is going to be pi r squared, or negative x squared plus 4 over 2 squared, divided by 2. Voila, there's our formula. We've set it up. Again, you can just punch that into the calculator. Be really, really, really careful with your parentheses. So we've got pi, in parentheses, negative x squared plus 4, whole quantity divided by 2, then that whole quantity squared, and that whole thing divided by 2. So I've got one parenthesis around this numerator here, squared, that whole thing in parentheses, squared, that whole thing divided by 2, multiplied by pi. Okay, variable is x. We're going from negative 2 to 2. And there we are. So there are 2 more problems and then we're done. We're going to find the volume of the solid whose base is the area bounded by f of x equals the square root of x, the x-axis, and the line x equals 9. Oh, and whose cross sections perpendicular to the y-axis are rectangles with height 2. Okay, so first thing we're going to do is we're going to sketch our area. So this is the square root of x. We're talking about the x-axis right here, and the line x equals 9. Now we notice the cross sections are perpendicular to the y-axis. So the y-axis is over here, so that means we're drawing it this way. This is dy, and when we set up our integral, it's going to be with respect to dy. Now as soon as I see this y, I know that all of these have to be in terms of y. So f of x, that's y equals square root of f of y. Okay, check. X of 9, that's the same as saying g of y equals 9. And then this right here, this is y equals 0, because that's the equation of this line for the x-axis. So what I'm seeing is I'm going from here where y equals 0 up to here where g of y equals 9, and f of y equals y squared, so y squared equals 9, y equals plus or minus 3. This is clearly a positive value for y, so this must be the point something comma 3. And now I've got to figure out what this is. I'm always going to do right minus left, so this is 9 minus y squared. However, let's see what we do with that. So these cross sections are rectangles with height 2, so I'm going to draw my little height here. We know that this distance is 9 minus y squared, and we know that this distance is 2. So the area of this base is just going to be 2 times this distance, 9 minus y squared. Where that's coming from, volume is start to stop, area of base times width. Don't mind that we're kind of using width in two different ways here. This is just the area of the base, length times width of a rectangle, and then this is our little dy, just like we normally do. So we've got that. Easiest just to use a calculator on it. 2, 9 minus y squared, comma y, comma 0, comma 3, or 36. So for our final one, let's find the volume of the solid whose base is the area between the x-axis, the y-axis, and the line 3y plus x equals 12, and whose cross sections perpendicular to the y-axis are equilateral triangles. So we start by drawing it. So I've got the x-axis and the y-axis. This should be 3y plus x, not 3y plus 7. And if you're not quite sure how to draw that line, you can either get y by itself or get x by itself, or you can just say when x is 0, so when x is 0, y is going to be 12 divided by 3, or 4, so I'm going to have the point 0, comma 4 up here. And when y is 0, x is clearly going to be 12, so I have the point 12, comma 0 down here. I can just draw my line right through that. This is the line. 3y plus x equals 12. So the area that we're looking at is going to be right here. Cross sections are perpendicular to the y-axis, so that means we've got a dy. We're going in the y direction, so we're going to have a starting y down here at 0, a stopping y up here at 4. So it was useful if we graphed this by plotting these 2 points. Otherwise, we just have to plug in and find them now. And we know that cross sections perpendicular to equilateral triangles. So we're going to need this. We're dealing in terms of y, so that means everything should be a y. This should be 3y plus f of y equals 12. F of y equals 12 minus 3y. So to find this area, we're going to do the right side, so that's 12 minus 3y. And then we're going to subtract this which is just the line x equals 0, or let's call it g of y equals 0. So this is 12 minus 3y equals 0, or just 12 minus 3y. Now, cross-sections perpendicular to the y-axis are equilateral triangles. So we have a nice little formula that we should have just memorized for the area of an equilateral triangle. I'm going to set this up. If we look way back over here, the area of an equilateral triangle is root 3 over 4 s squared. We can see that our side is this 12 minus 3y. So I've got root 3 over 4 side squared 12 minus 3y. That will be Math 9, square root of 3 divided by 4, 12 minus 3 alpha y squared, variable is y, 0, comma 4. On some of the calculators, you're going to need to put this fraction, root 3 over 4, in parentheses. It doesn't hurt if you do it on the 83s, but on the 82s, I think you have to do it that way. And there we go. So, this concludes Geometric Applications 5 notes.